All right, so let's see how we can use this difference of Gaussian. Okay, so what you do is you first like blur your image with the Gaussian kernel with a standard deviation of sigma. Okay, so this is like the pre-processing step. Then you again blur your image with a different Gaussian kernel, which is k times sigma. So k is your scales, like how you are varying the standard deviation of your Gaussian kernels. Okay, and then you simply subtract 2 from 1. Okay, so this is your image, and this is you have smoothened this image using Gaussian kernel, the first Gaussian kernel, and this is like the second Gaussian kernel, which has a slightly bigger standard deviation. That's why it's blurry. You subtract these two, you got this image, and this is exactly like what you will get if you smoothen your image using a Laplacian of Gaussian kernel. Okay, so that's like a very, very interesting approximation. Now, how you can use that when you are computing features for SIFT? You can simply use like multiple scales of Gaussians, right? For example, in this case, you have just sigma and k sigma, but you can have multiple scales. You just keep multiplying with k, which is like the multiplicative factor, and you can compute like smoothened images like these. Okay, so that will be your smoothened image, and then you can just keep subtracting them. Okay, so this is subtracted from this, and again this is subtracted from this. So you keep doing that over multiple scales, and these are your response function, or you can say like response activations after difference of Gaussian, and this will be like a approximation of your Laplacian of Gaussian as well. Okay, so this is like the same step which we discussed right over here. Okay, and then we perform this operation on those heat maps to get the list of key points. But here you will see like you have a different stack as well, and this is called octave. So in this octave, you have multiple scales. Now what you do, you like stack multiple octaves on top of each other, and the difference is, in this case, you were changing the size of the kernel, right, the Gaussian kernel, but you do that for different resolution of your images. So in this case, you are reducing the resolution of your image, and you keep doing that. You can have multiple octaves. So now you can see that you are actually making this algorithm scale invariant from 2 point of view, right? So the first is you are actually using your kernel, which has a different standard deviation. So that's taking care of multiple scales. And you're also performing filtering on like differently sized images. Okay, so at 2 level, you're actually taking that into account. And again, you will repeat like the same process for this stack as well. And again, from this, you will try to find out the key points. Okay, so yeah, this is just like trying to visualize the steps I showed you earlier. And you smooth your image, and you get like, again, you smooth from a different standard deviation, you subtract. So you can keep doing that, okay, as you increase your standard deviation. Right. And at the end, you will take these and you will figure out what are the key points. Again, this is the same step. It's nothing new. Okay, so for each pixel location, you're just trying to figure out whether this is maxima or minima. If it is, that will be list of key points. So once you do that, then the result you will get will look something like this. So all the yellow circles over here were actually detected as key points using the filtering operation, which we discussed in the previous slide. Now you might like see one interesting aspect here, right? So these key points have like the scale factor as well, because the radius of the circle which you are plotting, it's actually varying a lot. You have smaller circles, you have bigger circles, right? So that size of the circle is actually representing the scale. So at what scale you are actually detecting this key point. All right. And what may happen is like at one location, you might have multiple scales as well. So that key point could be like being detected as key point for varying scales as well. So that's why you can see like it's actually cluttered at this location so you have like all these key points here, right? And you can see you have smaller ones, then you have bigger ones. Okay, so this will be like a long list, of course, because this was done at like multiple scales and multiple kernels. As I said, like 2 different aspects there.